Good morning, everyone. Of course, it is morning in my house. Not sure what time it is in your house, but welcome to week 7. It is Monday, April 27th, and this is week 7 since we have been apart. And this is the Kruscal-Wallis Test. It is the non-parametric partner to the ANOVA test. You remember the ANOVA where we had the 3 sets of data and we wanted to see if the means of all of the 3 sets of data were the same or if one of them is different. This is the same thing, but because the data here is not normally distributed, we can't use the ANOVA test, and we work with the ranks. This is very similar to the Wilcoxon rank sum test that we did 2 weeks ago. It's just that it has 3 sets of data, and instead of just finding the ranks of the smaller class size, we have to find all the ranks. This is kind of arduous. It's, it takes some time, but it's really easy. This is our last one with a big, giant, ugly formula. And then after this, we've got only 2 tests left. One that uses a calculator and one that does not. So that's going to be the first 2 weeks of May. We will finish our last 2 tests, and then we'll just review, and hopefully by the end of May we'll be done. You'll have your final, and sadly, our time together will be done. Anyways, back to the Kruscal-Wallis test. Continue to check before I'm just going to butt in one last time. Continue to check eSchool just to make sure that the assignments that you're handing in, I'm getting and I'm grading and I'm putting them in. So if for some reason you submit something, I don't respond and say, hey, it looks good, or you don't see it on eSchool, just let me know, because sometimes it gets lost in my email or I can't find it in Google Docs or whatever. So this is our first Kruscal-Wallis test that we're going to try to do. And since it's morning time in my house, and I've been having cereal for breakfast over this break, Monday through Friday, here are 4 different brands of cereal. And we want to know, and these list the calories in one serving of 4 different brands of cereal. Normally, we only do ANOVA or Kruscal-Wallis with 3. This one had 4, and I thought I'd just do 4. You'll notice the sample sizes are all the same. They don't have to be all the same. So you are going to do number 1. And when you do number 1, I added a 550 here, so they would not have the same sample size. So you can do one with 3 samples, one with 4 samples, one where the sample sizes are the same, one where they're different. The only thing that's the same is they both have that alpha of 0.05. So this is the data that I have. And you take all that data. There's 4 lists. There's 6 numbers in each list, so there's 24 pieces of data. I will post this picture of this page on the server. And that's what I did, is I put all data goes in one big list. Because the data is independent, there's no cereal brand 1 that's also a brand 2 that's also a brand 3. They're not before and after you add the milk or whatever. They're all 4 separate different types, so they all go in one list. And just like ANOVA, the HO is there's no difference in the number of calories a serving in the 4 brands of cereal. And then H1 means this, again, just like the ANOVA, will tell you whether all the brands have the same number of calories statistically, or if there's a big difference between one or the other. The difference here is, if you recall back with ANOVA, we had that Chauffet test that we had to go through with that awful formula that told us where the differences were. We don't have that here. The Kruscal-Wallis test will only tell us whether the calories are the same or different. We don't have a procedure here in this course to identify where those differences are. So you're going to sort, you put all the data in one big list, sort it, small to large, group it, so we know which data value goes with which group, and rank it, just like we did in the Wilcoxon rank sum test. In this case, the sample sizes are the same, but they don't have to be the same. Now here is, I'm just going to do it one at a time, show you each column at a time. Here's my data. It's all in one list, and I sorted it. Then I started to group it. So there's your A's, your B's, your C's, your D's. I matched them all up. You'll notice there's two 1/16s here. It doesn't matter if your data says DC and mine says CD. When I first found that C, I could have put the C for that 1/16 or this 1/16. It doesn't matter. But you'll notice there are two 1/16s. So when you go to rank, these are sharing ranks 9 and 10. Down here, these two 125s, because this goes to rank of 16, this shares 17 and 18. This is going to share 19 and 20. 130 shares 21 and 22. And I put a little check. When you finish, there's 24 total pieces of data, and when your rank is 24, great. That means, for the most part, it looks pretty good. You cannot have, if you have two data pieces that are the same, they cannot have different ranks. You cannot give two data values that are the same two different ranks. They have to be the same. And statistically, when we rank, they should be the average of the ranks they would have been had they been different. Okay, now, in this case, in the Wilcoxon rank sum test, we only had to find the sum of the ranks of the smaller sample size. Or, if the two sample sizes were the same, we found the ranks of either one. In the Kruscal-Wallis Test, which has this big, long formula, you need to find the ranks of each one. And you got to tell me what you're doing. You can't just have numbers thrown on the paper and shazam, here's your answer. It's got to be organized. So I know that brand A is rank 1, brand B is rank 2, C is rank 3, and so on. And then if you go back to your numbers, I just took, for rank A, I just took the ranks 4, 7, 13, 17 and a half, 24, and I put them in a list. Now I would try to organize this, because when I did this the first time, whoops, I know there's a little glare there, I'm going to move it. Here's my data. Here are those ranks for A. Here in 3 are the ranks for the B's. Like these are the B's. B was 1, B was 2, B was 6, and I put the A's, the B's, the C's, and the D's here. There's 6 numbers in each list. And I kept them there because when I did this test the first time, I came out with the wrong test statistic. So had I not kept all of these, I would have to fill these in again and try to figure out which one it is. Lucky for me, it was in rank 1 where I think I put like 13 and a half. One of these numbers was off by 1. But keep all this data here until you finish, so you know your answer is right. And it's just a little easier to check. If your test statistic doesn't come out to what it's supposed to be, or I tell you that my test statistic is 1 and yours is different, my ranks aren't the same as yours, you can go through and just check if your data is all there. All the sample sizes are the same. Notice these are all little n's because they belong to each individual sample. And then big N is the total number of data values altogether. And way back from, we used K when we did the F test. K was the number of groups you had, and the number of groups we have here. When we did the ANOVA too, when we did the Chauffet, we had number of groups. K was always 3. Here K is 4. Now here is the test statistic formula. Remember, we don't have any tests in the calculator anymore. So all the tests are formulas. And again, I'm going to post a diagram of this. This is your procedure table. We stated the hypotheses. We have never really identified the claim, but they're asking us if the if there's a difference. So the claim is really HO. We always, at the end, go back up and answer that question. The critical value we'll come back to in a little while. We arranged the data, we found the sum of each rank, and here's your formula. Just like the F-test with degrees of freedom, it uses an H value. 12, you'll notice back when we did the Wilcoxon rank sum test, 12 is a constant number that we use in statistics. So that 12 is always going to be a 12. That 3 is always going to be a 3. What's going to change is the big N. Now, I'm pretty sure you guys are bright enough to put, if N is 24, you can put 25 in here and not put 24 and 24 plus 1. It just makes it a little more complicated. So I put a 24 where I saw an N because there's 24 pieces of data. I put a 25 here, and then I put my 4 ranks. So when I added all those up, they were here, and then you have to square each one of them because this is going to use a chi-square critical value. It's non-parametric. Here are your 6, 6, 6, because all my sample sizes are 6. That's a minus, that's a 3, and again, this is a 25. These two numbers are 24 plus 1, which is 25. I put those numbers in, and it looks like this. There's my 12, n times, this is n plus 1. Here are my ranks squared. See how I kind of erased that? This was, originally I think I had 78 there instead of 79, but it's easy to find if you just keep all those numbers in your list. These are my ranks, squared them all, divided them by 6. It is crucial that you put these 24 times 25 in a parentheses because it's got to take that 12, multiply these up, divide this, and then take that number and multiply it. I wouldn't put this in and get a big, long, ugly decimal and put this in and get a big, ugly decimal and then try to go back and multiply them together. I put this in my calculator, and I'll show you, as one big, long number. That way, if you have to change it, you can just go back and edit it, and it's pretty easy. And I gotta find my calculator because I think it's still in there. If I get out of here, there it is. There's my 12 times, just like it's there, parentheses, a big set of parentheses, and then a parenthesis around the denominator, times 79, and I'm going to hit this again so that I can arrow back. And then I put each, there it is, my 12 divided by 24 times 25 is in parentheses. That whole first term is in parentheses. There's my rank 1 squared divided by 6 plus rank 2 squared divided by 6 plus rank 3 squared divided by 6 plus rank 4 squared divided by 6. You can stop at 3 when you do yours because you'll only have 3. Minus 3 times 25 and 2.842, because this uses the chi-square test table for the critical value. It uses the chi-square distribution, so I needed 3 decimal places. You have table G, but I may post it again because I posted it way back. It was third quarter, one of the first things. So I will post again this. Degrees of freedom is K minus 1, which is going to be 3. Alpha is 0.05. This is always right tail because we're squaring everything, making everything unusually big. And your critical value should be, here's an oldie but goodie, the table G. I'm finding it. It's here. There it is. Table G, 3 degrees of freedom, right-tailed, 0.05. There it is. There's your test statistic. Now, you don't really need to do a diagram. You'll notice that your test statistic is really small. When you look at your groups, you'll notice there's B's at the top, the middle, the bottom. There's C's at the bottom, the middle, the top. There's D's. They're all pretty well distributed. It's not like there's a whole bunch of A's at the top and a whole bunch of D's at the bottom. So it looks like they're kind of spread out. There's a 50, 60, 70. This looks a little big, but it's not statistically big enough to make this test statistic large. But I did do, if you recall back when we did the chi-square, it was a skewed diagram. I started with 0, and I did do a diagram so that you can see we are, of course, in our happy place. I did not reject. Therefore, they asked us, is there a difference in the calories per serving of the 4 different cereals? And we are saying no, that it appears as though statistically the number of calories in the cereal are statistically equal. So we cannot support the claim that there's a difference in the number of calories per serving of the 4 brands of cereal. Now, I did it on 4 sheets of paper. I wanted to kind of spread it out. I do have a form, but you can't fit on the, like one side of the form is the table and the other side is the formula. And the formula takes a whole long sheet of paper. So it's probably easier to put the data on a sheet of paper. If you want to put the formula, you may want to write the formula sideways because it fits. Because if you try to squish this big thing in this little amount of space, it's going to be trouble. So if you could please do number 2. It has 3 sets of data. Remember, I added that one 550 that was in there. And if I can find it real quick, I'll show it to you again. Eli, quiet. Give me 1 second. I'm almost done here. Here it is, here it is, here it is. Don't go anywhere. Keep watching. Yeah, there's your number 2. You're going to talk about the mathematics literacy scores in the 3. Don't forget to add the 550. So you're going to do number 2. Today is Monday. I'll probably check back in. This is all I have for this week, this one test. If you want to try to do 3, if you want to try to do a couple of them, talk to me. Let me know what you're doing. Check eSchool. Stay safe. Try to get outside if you can stay away from people, maybe take a walk. Let me know how you're doing, and I will see you again. I'll probably post something maybe Thursday or Friday to remind you that this is due, and maybe just give you an outline of everything we've done so far and what you should have handed in for the 4th quarter. Okay, take care. See ya. Bye-bye.